Mountain climbing. Mountaineers often use a rope to lower themselves down the face of a cliff. This is called rappelling. They do this with their body nearly horizontal and their feet pushing against the cliff. So the body is nearly horizontal, makes a small angle with the horizontal. Suppose that an MC mountaineer mass 82.0 kilograms climber who is h equals 1.90 meters tall and has a center of gravity delta hcg of 1.1 meters from his feet rappels down a vertical cliff with his body raised delta theta of 35 degrees above the horizontal. He holds the rope LR equals 1.40 meters from his feet and it makes a 25-degree angle with the cliff face, so with the vertical. Part A, what tension does this rope need to support? Now, if I look at the forces acting on the climber, there is the tension making an angle beta with respect to the vertical axis. There is the weight mcg. There is the normal force applied by the cliff face, and there is a static friction which avoids the slipping of the climber. And so to be able to draw the free body diagram for the climber, we have to identify all of these forces. So we have tension, weight, normal force, and static friction, whose direction we generally do not know. We assume it's in the plus y direction. So this is our coordinate system, x, y, and z. All right, so let's draw the free body diagram for the climber. Now, we were told that the climber holds a rope which is 1.4 meters from his feet, while the height of the climber is 1.9 meters. So we have to draw a tension at a distance 14 over 19h from the feet, from the climber's feet, making an angle beta with respect to the vertical. And at the same time, the center of gravity of the climber is at 1.1 meters from his feet. So it is at 11 over 19h from his feet. It is pointing down in minus j hat direction. And if the climber makes a horizontal, an angle of delta theta with the horizontal axis, if you complete this, you see this is 90 minus theta, this is theta. So delta theta is the angle the weight makes with the normal to the climber's body. And that same angle, delta theta, is here. So if this is the vertical axis, this is the horizontal axis. This is 90 minus delta theta. And then we have the tension making an angle beta plus 90 minus delta theta with respect to the climber's body. And in addition, we have the contact point normal force and static friction pointing up. So we have drawn all the forces acting on the climber. Now in part A, we were told to find the tension that the rope has to support. Now, in order to find the tension, the easiest thing here is basically to eliminate the effects of these two forces from our equations, which we can do by considering the torque with respect to the contact point or the pivot point. So we consider the torque with respect to the contact point to eliminate two unknowns, static friction and the normal force. Okay, the net torque should be equal to 0 in at equilibrium. The net torque will be having a components due to the perpendicular component of the tension with respect to the body of the climber. Now, what is the perpendicular component of the tension? Now, the tension makes an angle with respect to the body of the climber, beta plus 90 minus delta theta. Therefore, the perpendicular component will be sine beta plus 90 minus delta theta times t. And it is applied at a position 14 over 19h with respect to the contact point. So r cross with perpendicular component. R cross f, or r multiplied with t, sine of the angle with respect to the body, will give us the torque. And using the right hand rule, we see that the four fingers point from the contact point to the point of application of the tension. Curl the four fingers towards the tension. The thumb points out of the board. So the first rotational effect comes from the tension for 14 over 19 H multiplied with perpendicular component of the tension T sine beta plus 90 minus delta theta. The second torque comes from the weight, and you can see that the weight has a perpendicular component with respect to the body, mcg times cosine delta theta, and it is at a distance 11 over 19h, and the sense of the rotation here is clockwise. Here it is going to be counterclockwise, so this will be negative, so minus 11 over 19 h multiplied by the weight mcg cosine delta theta, and the net torque has to be equal to 0 at equilibrium. So if I multiply, so let me get rid of these h's here and these 19s here. So I'm left with an equation 14 tension sine of 90 minus delta theta minus beta minus 11 weight mcg cosine delta theta equals to 0. There is only one unknown here, and here I can recognize 14t. Sine of 90 minus an angle is cosine of that angle, so this is cosine delta theta minus beta minus 11 times the weight mcg cosine delta theta equals to 0. So this gives me the symbolic answer for the tension to be 11 times the weight mcg cosine delta theta divided by 14 cosine delta theta minus beta. Okay, now we can substitute the numbers. The weight of the climber mcg is he's 82 kilograms, so 82 times 9.8, it is 803.6 newtons. Delta theta is 35.0 degrees and beta is 25.0 degrees. So if I substitute these numbers, I obtain tension is equal to 11 times 82 times 9.8 cosine delta theta cosine of 35 degrees divided by 14 cosine of 35 minus 25. And this gives me my final answer for the tension to be 525 newtons. Let's move on to part B. Find the horizontal and vertical components of the force that the cliff face exerts on the climber's feet. So horizontal component, normal force; vertical component, static friction. Now if I write the equilibrium condition on the x-axis, net force on the x-axis should be equal to 0. I see that I have the normal force and the horizontal component of the tension, which is going to be t sine beta, so it makes an angle beta with respect to the vertical, so the horizontal component will be t sine beta. So I have the normal force minus T sine beta is equal to 0. So I find that the normal force is T sine beta, or the normal force is, since I know what T is, 11 mcg cosine delta theta sine beta divided by 14 cosine delta theta minus beta. That's the symbolic answer. Now, if I substitute the numbers, the normal force is equal to tension times sine of 25 degrees, which gives me a normal force of 222 newtons. Now we can talk about friction. The net force on the y-axis should also be equal to 0. So if I look at the forces on the y-axis, I have T cosine beta, vertical component, static friction, and the weight. So if I write this, static friction Fs plus T cosine beta pointing up and the weight pointing down minus mcg equals to 0, this gives me for static friction mcg minus T cosine beta. So this can be rewritten as mcg minus my symbolic answer for tension, 11 mcg cosine delta theta cosine beta. So I'm substituting for the tension here. And then I have 14 cosine delta theta minus beta in the denominator. So this gives me my final answer if I write this with common denominator for static friction. I have mcg times 14 cosine delta theta minus beta minus 11 cosine delta theta cosine beta divided by 14 cosine delta theta minus beta. So if I substitute the numbers here, the static friction is 82 times 9.8 minus tension times cosine 25 cosine beta. This gives me a static friction of 328 newtons. So it is positive, therefore the direction that I have assumed is correct. Let's move on to part C. What minimum coefficient of static friction is needed to prevent the climber's feet from slipping on the cliff face if he has 1 foot at a time against the cliff? Okay, now this is the static friction we need in order to avoid slipping. Now, if this is the maximum possible value of the static friction, that is equal to mu sub s times n. If mu sub s has its minimum value that satisfies this, then it's going to have this value. If the maximum value of the static friction is greater than this, then you can have a larger static friction coefficient. So this is basically what we need to avoid slipping. So therefore we need a minimum mu sub s value so that the maximum value of static friction can be equal to this. Okay, so minimum static friction coefficient is the static friction force divided by the normal force. So it's going to be equal to, now we have the static friction here that we have calculated, mcg parentheses 14 cosine delta theta minus beta minus 11 cosine delta theta cosine beta divided by 14 cosine delta theta minus beta, and then we have the normal force 1 over the normal force. It's 14 cosine delta theta minus beta divided by 11 mcg cosine delta theta multiplied with sine beta. So let's remember our normal force. Here it is, cosine delta theta sine beta, 11 mcg divided by 14 cosine delta theta minus beta, but this is the reciprocal. So I can see that these two will cancel, and I will find the minimum value of the coefficient of static friction. Let's see here. We have also the mcg's canceling. So I'm left with 14 cosine delta theta minus beta for the static friction. Now, instead of 14 cosine delta theta minus beta, let me open up this cosine a minus b. So it is 14 cosine delta theta cosine beta, and then plus 14 sine delta theta sine beta. That is equal to cosine delta theta minus beta. And then I have minus 11 cosine delta theta cosine beta divided by 11 cosine delta theta sine beta. All right, so I can see that I have a 14 cosine delta theta cosine beta and 11. So if I subtract this, I obtain the final answer for the minimum coefficient of static friction. It is 14 minus 11, that is 3 cosine delta theta cosine beta plus 14 sine delta theta sine beta divided by 11 cosine delta theta sine beta. So that is the minimum coefficient of static friction I need. If I substitute the numbers here for delta theta and beta, so remember we have delta theta 35 degrees, beta is 25 degrees, I obtain the minimum coefficient of static friction to be 1.48. So that is my numerical answer to this question. Okay, so to summarize, we have we're talking about the rappelling procedure. A mountain climber holds his body almost horizontal and is basically supported by a rope, and the slipping of the climber is avoided by static friction in this setup. Now, knowing the location of the center of gravity, the location where the rope is attached to the body, and the normal and static friction forces, here we can draw the free body diagram, and we note the point of application of each force at 1.1 meters from the feet, 11 over 19h, because 1.9 meters was the total height. We have the center of gravity at 14 over 19h, or 1.4 meters from the feet. We have the tension. And the climber makes an angle delta theta with respect to the horizontal, 35 degrees above the horizontal, and the rope makes a 25-degree angle with respect to the cliff face, that is the vertical. So that this is the cliff face, so this is the vertical, so that's the angle beta. The first thing I did was to calculate the torque with respect to the contact point to eliminate the effect of these two forces to find what tension is. First, I see the sense of rotation due to tension is counterclockwise, but due to the weight is clockwise, so they have the opposite sign. The net torque should be equal to 0. So the point of application, 14 over 19h, R cross with F, I need the perpendicular component of the tension. So it is sine beta plus 90 minus delta theta. Minus, because it's the opposite sense of rotation, mcg cosine delta theta, perpendicular component R cross F, 11 over 19h is the distance. I calculate the tension. And I substitute the numerical values, I obtain 525 newtons. Now for the equilibrium on the x-axis, the normal force is balanced by the horizontal component of the tension, which is T sine beta. So that's what I use. And for the equilibrium on the y-axis, the static friction is balanced by the weight and the vertical component of the tension, which is T cosine beta. And that must be equal to 0, so I calculate the static friction. Now, this is the static friction I need. If the maximum value of the static friction is less than this, then the friction will not be successful in avoiding the slipping, and the climber will start slipping down the cliff face. Now, if the maximum value of the static friction matches this, so that means you need a minimum coefficient of static friction to have this equation hold, then you can see that there will be no slipping. So if I substitute for static friction and the normal force what I found in part B, I can see the static friction is given by this expression, which has a numerical value 1.48. If the coefficient of static friction is greater than this minimum value, then that means having this static friction has not reached the maximum value yet, so this static friction will hold and will avoid the slipping of the climber.